To get a sense of how variational approximation works, we'll use a simple multivariate Gaussian example and show the results. So to set up the problem, suppose we want to approximate a Gaussian. And this will be a function of these latent variables. So there's variables that we don't know about this. And in fact, they're going to be parameters of this Gaussian. And the parameters are given by mu and lambda, where lambda is the precision and mu, of course, is the mean vector. Now, as we saw in the last class, we can approximate this using a mean field factorization, which basically says that we take those z's, that z vector, and we parameterize it in terms of its components, which we're calling z1 and z2. So it's a product of the distributions for each one of those components. Now we're going to use the result that we found last time concerning optimal variation. And basically that says that we can iterate over each one of those variables, z1 and z2, one at a time in order to get the result. So we can start with z1, and if we start with z1, we only need the terms where z1 is actually in the expression. We don't need any of the other z2 terms there. However, we will actually take the expectation through once we get this expression of z1, which is shown here. We'll take the expectation through for z2. And in the end, we get the result shown, which is a quadratic in z1. So the quadratic then suggests that this is a Gaussian, and we find the distribution then for z1, which is to be Gaussian. We can get a similar result. Obviously, these things are symmetric, so we'll get a similar result for z2. So z1 and z2 then are both Gaussian distributions. So note that this Gaussian result came strictly from our result before, which was for Kullback-Leibler minimization or elbow maximization, and not from any other assumptions. So this is kind of a neat result. By completing the squares, we see that we get these Gaussians for both z1, where the mean for z1 is shown as a function of the original mean for mu1 and the components in the precision matrix. And by symmetry, z2 is also Gaussian, as we said, and with a very similar, with basically the same form. So the result then came directly from this minimization and not from any other assumptions that we made about the inferential problem. And we typically solve this through iteration, but here we solved it very quickly as a closed form. And in the next class, we'll actually go through and see more complicated examples that we'll use an iterative solver to get results. And we'll describe those iterative solvers and what they look like in terms of available libraries today. But for now, let's look at this particular result by looking at some simple code that shows what the approximation of this Gaussian looks like. So here's the setup for our problem. We load the packages that we need. Our goal is to find this Gaussian with uncorrelated variables that minimizes the KL divergence or maximizes the elbow, and we're going to do it for a full rank Gaussian. In other words, one that in fact has off-diagonal terms. And the cells below give the details of that. Let's take a look at the picture. Here's the Gaussian that we're trying to approximate. Now, in this particular case, we don't need to do any iterative solutions. We can just find a closed form solution since this is a Gaussian. The approximating distribution is shown in red, and the target distribution is shown in blue. The approximating distribution does a pretty good job, but it is clearly too constrained in the sense that we told it the off-diagonals had to be 0. And in the next class, we'll see that we can do a better job of approximating when we don't over-constrain our solution. But this does give us an idea of how the variational method approximates a target distribution.